More than 9 decades of serving the nation. Central Board of Irrigation and Power.
So, yesterday we have seen the load flow studies. Today we will discuss this power system stability studies. This is also a mathematical tool. Mathematical tool to study the stability. Now, what is the stability against? In load flow study, we said things are a steady state. Steady state is a state, shall state, like driving a car at a steady speed. Now, here we are talking of the dynamics, change. A change can be slow change. Change can be sudden change, fast change. So whether the system keeps on operating in a steady state even after the change, that is the basic question. Okay, so moving from one steady state to another steady state. The system is working at a steady state. Now we want to move from one steady state to another steady state. Just to give a physical example, let us say a man carrying around 50 kilograms load on his head is going from one place to another place, moving very slowly at a speed of, let us say, 10 kilometers per hour. Suddenly you say it's too slow. It will take a long time to reach. You just double your speed. From 10 kilometers per hour to 20 kilometers per hour, carrying a load of 50 kilograms on head. He may do it slowly. If he tries to do it quickly, he will fall down. So that is the scenario. From moving from one steady state to another steady state, whether he is able to do it or not, whether he remains stable, he reaches another steady state without disturbance, because the system, whole system is operating in a very delicate condition. Generation balanced with the load and losses. Okay, so we will look into the dynamics of the system today. So, basics of power system stability, definitions of some terms. Some terms are basically connected with the stability, but they are having different meaning, like stability, security, reliability. These terms are used interchangeably, but they have a different meaning. Then dynamics of the generator is important while studying the stability. Then generator connected to the power system, how it behaves, and power system dynamics and equal area criteria. I think you must have heard these names in the undergraduate. So today, basically, as we have done yesterday, we are not going into the mathematics much. We'll write down certain equations, try to understand their physical significance. Okay, only the physical significance and practical importance of the things, how they can help the practicing engineers, not on how to perform the study. These studies, calculations, they can all be done by, as I explained yesterday, by a software. And these softwares are available in the market as a package. Only one should know how to operate them. What is the input data and how to interpret them. So we will only try to understand how the system behaves. You can stop any time and you feel you're not able to understand. So what is the stable operator? and safe system stable. Stable means uh, man carrying a load of, let us say, 50 kilograms, walking smoothly without any difficulty. He has to balance the weight also. Anything disturbance can put him down. The same man, if you put a load of, let us say, 75 or 80 kilograms, he may fall down. You must have seen the weightlifting, no?
Yes, sir.
Olympic weightlifting.
Clean and jerk.
So clean and jerk. Jerk may the weight has to be put for some time. If you don't hold that weight for some time, 10 seconds or 15 seconds, I don't know. But if you are able to hold, then it's okay. Then you are done. But higher is the weight, or your margins are. You don't have much margins. So all generators connected to grid or operate at a synchronous speed. If let us say 50 generators are connected, all should operate at synchronous speed. Normal changes in the load are taken care by inertia of the rotating masses. What are the rotating masses?
Rotors.
Rotor, turbine in the thermal power plants. Huge mass. Rotor in a generator doesn't carry much mass. Basically, the mass is in the turbines, hydro power turbines. So they are huge masses. So these masses, when they are rotating at a speed, if they ask to lose the energy, they will slow down. Energy is proportional to the speed. So rather squarely proportional. So they will, if they lose the energy, they will slow down. If they slow down, synchronous speed will come down. If you unload them, reduce the load, then they will speed up. But in doing so, they are able to manage the small changes in the load. As I said yesterday, load keeps on changing. There is no control on the consumer desire. The whole system is made to feed the consumer. So there should not be any control on the consumer in a good electrical power system. So this helps. It helps in keeping the load constant. If these minor variations result into some relative motion of the angles, there are 50 generators acting. Different, they are having different inertia.
Yes.
Smaller generation will have small inertia, large generator will have large inertia. So if there is a change of, let us say, 50 megawatt, so 500 megawatt machine, it's hardly 10% change, not much. But for 100 megawatt machine, it's a large change because it has small inertia. So there will be relative motion between the generators' speed, rotor angle changes. There will be some changes. So these changes will be taken care by state governors because what will happen? The speed will ultimately either decrease or increase. And there is a governor to sense the speed and increase the output of a turbine, input of the turbine, sorry, input of the turbine. So this speed governor will restore the speed. The system frequency is maintained within the acceptable limits and supply to the consumer is maintained. So if you are able to do this, then you say you are stable.
So what are the maximum and minimum values of deviation allowed in the frequency terms? Like
This is plus minus 0.2 on the positive side, 0.5 in the negative side. But these are given in the CRC manual. CRC, there is a getting a name of the document. That document you can get, just put it on the Google. CRC Grid Code, National Grid Code. National Grid Code issued by Central Electricity Regulatory Commission, CERC. So the grid code gives the code of operation in the various systems. Systems means central system, state system. So how they should operate, how much frequency they can allow, how much voltage they should allow, what they should do, how they should connect, how the system should be planned. So many things are connected.
In the second point, you said that according to the load changes, the speed of the synchronous speed increases or decreases.
It depends upon whether load is increasing or decreasing.
So, but synchronous speed is the same throughout for whatever voltage.
Synchronous speed theoretically is the frequency. The speed is corresponding to the declared frequency. But if the declared frequency पे चल रहा है तो synchronous speed is same. But if the system deviates from the declared frequency, then the speed will change. Well, in a steady state, when you say all generators should operate at a synchronous speed, that's the ideal condition. When I say it's I'm stable, and minor deviations are taken care by the governors or system inertia itself, then I am stable. But this is an ideal condition. This will not happen if let's say suddenly a line trips or the machine trips. There is a jerk.
Only in case of fault.
It may be fault. We will come to that. We will come to that. We just hold on your question. It will come. Basically, we are discussing that only. Okay. So, what is essential for the steady state operation? Stable operation. Generator must keep synchronism. If there is a relative motion, it begins to change too much, uncontrolled oscillations may develop and they may cause damage to the generator. अगर ये control नहीं होगा. Okay. If this happens, then there are protective relays which will trip the generator. If the generator trips, then whatever output it was giving, it is lost. Then if it is lost, the stripping may prevent the damage to the generator is prevented, but as a result, there is an under frequency. There is a possibility of a load interruption, or in the worst case, cascading. Other machine gets overloaded. This also trips, and this phenomena goes like a virus, and the whole system collapses.
How does it result in under frequency?
If you are having a 10,000 megawatt system, and if a 500 megawatt machine is lost, so now your generation is 950 megawatt. Load is 10,000 megawatt. So sorry, 9,500. So the 500 megawatt, where from it will come immediately? From the rotating masses. Rotating masses will lose their energy. It will come down. Frequency will come down. Okay. If you generation is lost, then demand is more than the generation. If the demand is more than the generation, then there will be under frequency. If the demand is less than the generation, then there will be overflows. Okay. So, synchronous operation. When we call machine is in a synchronous operation, a machine is said to be in synchronous operation with the network with another machine to which it is connected. If the average electrical speed equals to the angular frequency of the AC network. Machine has a frequency, it's a prime mover frequency. Then there is a connected AC network. AC network has a frequency. If both are operate same, then it is machine is said to be in synchronous operating synchronously with the network. Whole power system is said to be operating in a synchronous machine if all the generators connected to it are operating in a synchronous machine. That is the ideal condition. Okay.
So slide थोड़ा वो इसमें on the basis समझ में नहीं आई कि average electrical speed equals to the angular frequency of the AC network. So थोड़ा सा समझो.
See, prime mover is operating, so उसकी speed है. But as I said, that there may be changes in this speed. Changes may be the result of changes in the load or governor is operating. So there will be some changes. Then there is a AC network, 50 hertz network. The 50 hertz network keeps its speed. That's the angular speed. So if this speed coincides with the average speed of a turbine, say, turbine is already, see both, see, abhi machine, can you just hold on for some more time? I'll just show you the generator, and when we discuss the generator dynamics, it will be more clear. Okay. Asynchronous operation. Asynchronous is which are not synchronous. Machines is in synchronous operation with the network or another machine to which it is connected if it is not in synchronous operation. If the speed is not matching, both the speeds are different.
So this will be a transient conditions.
This can be a transient condition, this can be unstable. The condition which leads to the blackout. It eventually results in the blackout. System need not run continuously in a synchronous speed. That is what I said, that system cannot operate unless there is a load dispatch center. And load dispatch center cannot operate independently unless there is a regulatory body. Otherwise, it will become dictator. And cost cannot come down unless there is a market. Market forces only bring down the cost, the competition. There has to be competition. So synchronous operation is a must for a grid to function. Asynchronous means either HVDC of course works in asynchronous mode because it doesn't work in any frequency. HVDC is the only thing which can work without frequency. Anyway, so a machine is said to be in hunting if it is continuously oscillating around the moving positions. Now coming to the disturbance. Basically, we are looking into the disturbance. What happens as I Example I gave, a person carrying a load of 50 kilogram on his head, walking at a steady speed. If it trips because of some obstacle in the road, somebody honks him, then he gets disturbed. So anything can happen. So a disturbance in a power system is a sudden change of or a sequence of change. Like you have said, there is a fault. The fault is followed by a loss of a line. Line will be, whichever the faulty line is there, which will be removed. So there can be a sudden change or there can be a sequence of changes. One or more parameters which disturb the system. So what are the possibilities? It can be a small disturbance, it can be large disturbance. What is considered as a small disturbance? A disturbance is said to be small, for which equations that describe the dynamics of the system can be linearized about the operating function. This is basically a mathematical term. If there is a dynamics, in a dynamic situation, if you can, while you are calculating how the data is changing with respect to time, if you can linearize the equation around its operating points without losing the accuracy of the calculation, then it is said to be small. And if you can't do that, if these equations cannot be linearized, then it is said to be a large disturbance.
Can you differentiate between the first definition there? One or more parameters and the operating quantities.
Yeah, one or more parameters. The power system parameters are basically the voltage, delta, P and Q. So one or more means any of
And sir, operating quantities.
operating.
Quantities.
Quantity means quantity is in the terms of magnitude.
Okay, right.
So does for how much time the fault persisted
It
can
will
also
all matter. It will all matter.
also be judgmental that
No judgmental, you can calculate. This is basically what you are saying is a critical clearing time.
yes sir.
That how much time the relay should take so that system remains intact.
Like sir, in a generator, in a
Yeah.
gas turbine, if it persists for more than 0.02 second, it is not limited within it, then the system becomes unstable.
Then this is critical. This is the critical. If you have to, critical means if this side is stable and other side is
Unstable.
so that's a critical clearing time. We will see all these things today. So what is the power system stability? This definition you might have seen in textbook also. Power system stability is an ability of an electric power system. It is an ability. The person carrying a load. If you can say this man can carry 50 kilograms of load for 10 kilometers at an average speed of 15 kilometers per hour. What it is its capability. Other man cannot do it. Oh. So this is the capability or ability. He is able to do that. So power system stability is a ability of electric power system. This is characterized for a power system. But this power system, the Indian power system, for a given initial operating conditions. For a given operating conditions are defined. Operating conditions means 50 kilograms of load. There can be another person who can carry 75 kilograms of load. These initial conditions are different. So, and still regain a state of equilibrium, operating equilibrium, keep on walking at a speed after being subjected to a physical disturbance. You can carry the load, it's one thing. But if I push him, can he still carry that load? He may or may not. अगर उसकी 50 kilogram capacity थी, he was loaded at that time was 25 kilogram only. He may unbalance, but still recover.
So the
Depending upon the initial condition. क्योंकि उसकी capacity तो 50 kilogram थी.
But the scenario would be different at if he is loaded with 50 kg weight and it's
Then
sudden jerk.
that is the initial condition. Initial condition उसको क्या थी? Ability तो है, that's the capability of the person. But initial conditions उसकी ये थी कि वो 10 किलोग्राम ही था उसके पास. So for it, given in initial conditions, subjected to the physical disturbance with a most system variables bounded. System variables do not change. Voltage, current, frequency does not change, and his practically the entire system remains intact. थोड़ा सा झटका लगा तो थोड़ा सा संभल के walk करना. So he has gone from one steady state operation to another steady state operation. बीच में उसको jerk लगा, but depending upon what is the initial conditions, he may or may not. So that is the power system stability. It's a capability, it's the ability of a system to withstand a disturbance given in weather and remain with all the system parameters bounded. मतलब इसकी सिंक्रोनस स्पीड पर चल रही थी सिस्टम, थोड़ी सी देर के लिए लाइन ट्रिप हो गई, machines got disbalanced. Maybe after some time, 10 seconds, 20 seconds, it's again operating at a steady state. With a different set of deltas. So it can be classified in three different ways: steady state stability, dynamic state stability, and transient state stability. We will see what does this mean. Steady state stability. It relates to the response of the synchronous machines to a very gradual change. So the disturbance here is not a very large disturbance, not a very sudden disturbance. Sometimes planned. Machine को अभी लोड बढ़ने वाला है, that is ramp it up, ramp the machine. So if it is a gradual change, load is increased, it is basically concerned with the determination of the what is the upper limit. कितना ये ले जा सकते हैं, जैसे कि पहले इसको 50 किलोग्राम लेके देखा, वेट लिफ्टर करते ना, उसके बाद 10 किलो बढ़ा दिया.
There are warm-up sets and then
And then you know basically
we can.
how much you can do. So if you do it gradually,
Chances of failure are less.
System remains.
and system will remain stable, and you can find out what is its limit, how much system can carry. This is steady state stability. Steady state because we have not made any drastic changes. Okay,